All right, so now we're going to look at forces, the second unit for our exam review. And really just at the beginning, you got to remember Newton's three laws of motions, F net equals ma. That's our key equation for the entire unit. Newton's third law is also important, that the equal and opposite is the other object. So if one object acts as a force, if object A acts in a force on object B, then object B acts at a force on object A, equal and opposite. It's the other object. It's never the same free body diagram. It's not on one free body diagram that both forces exist and cancel each other out. It's always the external object that experiences the force. So the earth pulls on me, I pull on the earth with gravity, okay? So, rules for free body diagram. This is a cornerstone, right? You should know this by now, review, but let's just go through all of the forces. You want to draw an arrow following all of these rules. Gravity always points down towards the center of the earth. All of the forces we talk about require physical contact. So, if there is a surface, then there are two forces you consider. There's a normal force perpendicular outward from the surface, and frictional forces are parallel to the surface, could be kinetic or static friction, but they run parallel to the surface. Normal force is perpendicular to the surface, right? And then there's a distinction between kinetic and static friction. Kinetic friction, if the two surfaces are rubbing or they have different velocities relative to one another, or static friction is they are not rubbing against one another. For kinetic friction, we have a formula for it. For static friction, we do not have. We have a formula for the maximum static friction. That is, if the frictional force were to exceed this, or an attempt to exceed it, then it becomes kinetic friction, okay? But this is not the amount of frictional force for static friction. It is the amount of maximum static frictional force that the surface can apply, okay? Static friction is a reactive force. That it responds, right? So the difficulty with static friction, probably one of the hardest things, is to identify the direction of the force. There's two ways you can identify. The easiest way is to think, or the most general way is to say, imagine there were no friction. Then how would the two surfaces rub against each other? Static friction would oppose that direction, okay? If there were no friction, which way would it go? Then static friction is going to oppose that. Tension forces are caused by a rope. So if there's a rope, it's always going to pull away from the object. And spring forces will always want to restore back to their relaxed length. There is a formula for springs that obey Hooke's law. Its force is proportional to how much it's stretched or compressed. But spring forces can pull or push depending on whether or not you stretched it and it wants to shrink back to its relaxed length, or you compress it and wants to expand out to its relaxed length. Drag forces are proportional to velocity. So these are air resistance, very common. It might be m times, a lot of the times it may not be proportional. For velocity or velocity squared or some other relationship you might have in here. The key part here is we always write it as F net equals ma, and the a we write as the derivative of the velocity, like in kinematics, and then we solve some differential equation by separation of variables. That's the general idea of a drag forces problem. Terminal velocity is when the net force is zero, because we're not going to go any faster or slower. That's the fastest we're going to go, because eventually the drag force equals whatever is causing the acceleration, and so then the net force ends up being zero at the terminal velocity. Okay, so overall process, all right, how do we solve free body diagrams? We want to identify the object or the system. We want to draw the free body diagram following our rules for free body diagrams. We want to identify the acceleration in the system. If it's moving in a circle, then there's centripetal acceleration directed towards the center of the circle. If it's kept in place or moving at constant velocity, the acceleration is zero. There's always centripetal acceleration anytime we're changing directions, okay, or moving on a circular path. There's a tangential acceleration if you're just speeding up or slowing down. If the acceleration's on an inclined plane, then we might need to rotate the axes so that x-axis is the direction is parallel to where the acceleration is, and the y is perpendicular to the direction of the acceleration. We then decompose force vectors into the x and y components. We assign positive and negative directions, and we apply F net equals ma. We sum the forces. We set it equal to ma. That's our general process. That's how we're going to handle pretty much any forces related problem. So let's go through a few here. So a heavy sign of mass m is held at rest by two supporting wires between two buildings, each with a wire making angle theta with the vertical, as shown in the figure. What is the tension in the wire? So let's go through our process. Draw our free body diagram. First, we start with gravity. We have mg. Okay. Then we say what's touching it. Well, there's wires touching it. So there's a tension force here. Okay. and then and that's an angle theta with the vertical, and then there's a tension force here. And then it's going to be the same, but we'll talk about why that is in a second. This angle is theta, okay? Boom. Anything else touching it? No, we're done with our free body diagram. Then what was the next step we wanted to say? We want to identify the acceleration of the system. Well, it's just hanging there. It's not accelerating up or down, not moving in a circle, so the acceleration is 0. Okay? Now we want to decompose forces. So we want to decompose the tension T1 into x and y component. This is going to be T1 sine theta. This is T1 cosine theta. Then we want to decompose T2 into an upward and a leftward force. This is T2 sine theta, and then T2 cosine theta. Okay? Then we're going to sum up in the x and the y directions. We'll assign positive. We'll say up's positive. We'll say right is positive. Then we're going to sum up in the x direction. F net's going to be 0 because there's no acceleration in the x direction. So T1 sine theta is to the right. T2 sine theta is to the left. And that equals 0. Those are our horizontal component forces. This ends up being T1 equals T2. So we know that these two have the same tension. In the y direction, upward forces, we have T2 sine theta pointing up, so it's positive. We have T1 sine theta pointing up, so it is positive. We have mg pointing down, so it is negative. That equals 0. We know that these two t's are the same, so we'll just call it t. So this will be 2t sine theta minus mg equals 0, and you can solve for t. It's going to be mg over 2 sine theta. Right? So that's going to be a there, like that. Okay, let's look at another one here. Experiment. 2 blocks are made of different materials placed on the same wooden board, which is initially horizontal. The table provides 3 values for the block: the mass, the area, the side of the block in contact with the board, coefficient of static friction between the block and the board. One end of the board is then slowly raised, which you'll find correctly identifies the block that will start sliding down the board first. It includes appropriate reasoning. So why will it begin to slide down? It has only to do with at some point, okay, if we draw our free body diagram, at some point we have a normal force, and then we're going to have a frictional force. That's what's preventing it from sliding down the ramp. Static friction. Now, eventually, our frictional force is going to equal the maximum static frictional force if we make the angle big enough, okay? And so what's going to happen is, and that maximum is mu times the normal force. So as you increase the angle, you slightly change the normal force. But here, it does not matter the area. The area is a misnomer. There's no aspect of friction that I described to you where we care about the area. We only care about which has the greater coefficient of static friction. And it turns out the mass doesn't matter either. So we can work this out. So let's kind of talk about this. First, what's the direction of the acceleration? A equals 0. So you can decompose it any way you want, but we might as well decompose this is the x and the y. That's pretty standard, so that this is, you don't have to do it this way, but this requires less decomposition. So what you're going to get here is, if you look at the net force down the ramp, it's going to be mg sine theta. Let's say down the ramp is positive. And then force of friction's up the ramp. That equals 0. Because it's like we're about to start accelerating. So the frictional force is equal to mg sine theta. And then the y, this is the x direction. In the y direction, if we say this direction is positive, then the normal force is in the positive y direction. Mg cosine theta is in the negative direction. That equals 0 also. So the normal force equals mg cosine theta. And if you think about your frictional force, it needs to be less than or equal to the maximum static frictional force. Right? So that means mg sine theta has to be less than or equal to mu s times mg cosine theta. And so what you're going to get here is the g's cancel, the mg's cancel. You get mu s has to be greater than or equal to sine theta over tan theta, which is tangent of theta, by the way. So what does that tell us? Doesn't really matter what the mass is. It's just who has the bigger coefficient of friction will allow you to have a bigger, this is cosine theta, allow you to have a bigger angle that you can drop it off at. So all that really mattered. The mass doesn't affect it either. It's just block 2 because it has a greater coefficient of static friction there. Okay. Let's look at this one. Let's see. A truck of mass mt is initially at rest with a load of sand, initial mass ms. At time t equals 0, the truck is pushed forward by a constant force F0, and the sand begins to leave the truck as shown. The mass of the sand has left the truck as a function of time is given by ct, where c is a positive constant with appropriate units. At time t1, there is no sand left in the truck, which you'll find graphs shows the velocity of the truck as a function of time. So we want to think about we're thinking about velocity. First of all, velocity versus time graph. The derivative of velocity is the acceleration. So the slope is going to be the acceleration. And we're going to think about F net equals ma. Because what's happening is we're applying a constant force. Okay, no other forces to the right. So if we look at just the x direction, we have our free body diagram. Let's just take a look at this. We have mg. We have a normal force. And then we have some F0 to the right. Okay, so in the x direction, we have F0 equals the mass. Now, what mass are we talking about? It's going to be the mass of the sand plus the mass of the truck times the acceleration. So what happens to the acceleration is, if you divide it by this, equals the acceleration. Now, what's happening is the mass of the truck that left is given by ct. So we're going to be losing some mass here. It's going to be, so we're going to do mt. It's going to be F0 over mt plus ms minus ct, because you're going to lose, the sand mass is going to reduce over time, so that's going to increase the acceleration, right? So look at this relationship. It's like 1 over t. So what's going to happen is it can't be constant slope, right? Because it's definitely got to, and the lighter it is, the more it's going to accelerate. So it's going to go up, and then at t1 there's no sand left in the truck. So once we're at t1, we're not going to keep losing it. We're not going to keep going faster. So at T1, the acceleration then is constant, because now we're not losing any more mass. Now all of these values are constant. So that's why C makes sense, because the slope gets bigger and bigger and bigger, and then it just stays at a constant acceleration once the mass is settled, right? And that's pretty much it. Let's look at this free body diagram problem here. Or sorry, this forces problem, free response question. So a small sled slides across a rough horizontal table with initial velocity v0. The coefficient of kinetic friction between the sled and the table is mu k. A string connects the sled to a device on the ground. The device maintains a constant tension in the string by unwinding the string as the sled slides to the right. The total mass of the sled is m. The string is attached to the device at x equals 0 and a height y here. The horizontal position of the sled is represented by x as shown in figure 2. Express all algebraic answers in terms of m, mu, ft, x, y, and physical constants. Derive an expression for the acceleration of the block at the time instant shut. So we're going to start with our free body diagram. It's our first step. Talk about gravity. Gravity acts downwards towards the center of the Earth. What's touching it? Well, you definitely got this string here. So this string acts at some angle. We'll call that ft. What else is touching it? The table. It's a surface, so it exerts a normal force perpendicular to the surface, and also frictional force, kinetic friction to the left, because the shoe is going to the right. That handles that surface. We have the rope. Nothing else is touching it, so we're done with our free body diagram. Now, which way is the acceleration? Well, it looks like the net force it's going to be horizontal, but probably going to slow down in this direction, right? Because it can't accelerate up or down, so it's got to accelerate right or left. So it's going to be accelerating left, because there's only components in the force to the left. This angle is theta. Now we want to decompose forces, set our positive direction. So we'll say left is the positive direction. Doesn't matter which way you want to say is positive or negative, but they just care about the acceleration itself. Actually, they said right was positive, so we should follow their convention here. Okay, so now let's do F net equals ma. In the x direction, that's going to be force of friction is to the left. Oh, we didn't decompose the tension. The tension needs to be decomposed into down and left. This is Ft cosine theta. This is Ft sine theta. Okay, so when you look at the frictional forces to the left, Ft sine theta is to the left. Actually, those are both negative because they're pointing left, and we said right was positive. Okay, Ft sine theta, that equals ma. And in the y direction, you have upward normal forces going positive. Ft cosine theta is pointing down, so that is negative. And then mg is pointing down, that is also negative. And that equals 0 because there's no vertical acceleration. It's only pointing to the left there. Now, the acceleration here, we can do it in terms of friction, but the friction is mu k times the normal force. So we're allowed to put equals ma. And notice we actually it didn't say we can use theta, so we're going to have to deal with that here in a second. So we need to get rid of the normal force here, but here we can solve for the normal force. It'd be mg plus ft cosine theta. So we can plug that into here. All right, so you're going to get negative mu k times mg plus ft cosine theta minus ft sine theta. And then let's just all divide it by m. and that will give us our acceleration. Now, it doesn't work because we have m mu k ft, but there's no theta in here, right? So we have m, g, mu k, the physical constant includes k, so ft, the theta is in here. So we got to look at the picture in terms of x and y. This is x, and this is y, so we got to think about a right triangle here, right? So the hypotenuse is square root of x squared plus y squared. So cosine of theta is going to be adjacent over hypotenuse, so we can replace that with y over that. So this is going to be minus mu k, and I'm just going to put a minus mu k mg plus ft, and then for cosine theta, we're going to say y over the square root of x squared plus y squared minus ft, and then sine theta is going to be opposite over hypotenuse, so that's going to be x over square root of x squared plus y squared. All of that divided by m, and that's going to be your acceleration, right? So the math got involved, but the process was pretty much standard, right? Everything we talked about in those steps are pretty standard there. Then the math gets a little involved, but there's that. Okay, derive an expression for the normal force exerted on sled as a table as a function of the position x. Well, we already did that here. We have mg plus ft cosine theta. So this one is probably pretty easy. And you just have to do ft being the cosine theta being x over the square root of x squared plus y squared. Oh, this should be as a function of, yeah, this is fine. This is as a function of position x. You're allowed to use these other variables are constant. X is the only thing that's changing in that scenario, right? Because the y is constant. It's not changing. The height of the table is not changing. Ft is not changing. They said that was constant. Mass and g are constant. Okay, as the system moves to the angle changes, briefly explain whether the magnitude of the acceleration system will increase, decrease, or remain the same in the block as he slides further to the right. So as the angle changes, what do we think about the acceleration? So let's reason that out from, you can reason out from this equation, okay? You could say, well, this can be a little tricky, but basically, you're going to increase the x component. This is maybe not such a great question. You know, the x component will increase because you're going to have more of a tension force, but the normal force will then kind of decrease a little bit because you're not pulling down on it as hard, right? So that there you'll see here. So as the theta increases, right, as theta increases here, cosine theta is going to decrease. So overall, this thing decreases. So the normal force goes down. That'll reduce the frictional force. However, sine theta will increase. Okay, because as you increase theta, so sine of 0 is 0, but then as you, sine of 0 is vertical. Well, in this case, 0 degrees is straight up and down. Sine of 0 is 0, but as you increase the angle, then that sine is going to increase. So this part gets bigger, this part gets smaller, so it kind of just depends a little bit. Overall, I would say like it might increase and then decrease, or at least explain it in words. So let's say the frictional force will decrease because theta decreases, because the theta increasing will decrease the normal force, and the component of ft in the x direction will increase. So it is impossible to say without knowing the relative values. Values of mu fn versus the ft, what do we say, ft cosine theta, right? So it's going to depend a lot on how those change. So this is a question I wrote, or it probably didn't work it out well enough for this review. But so there's not a right answer for this one. Just understand. All I wanted you to understand in this part of the question was just like, how are the different forces going to change as the angle increases there? Okay. Let's look at this problem. We have a block at mass rest m is attached to a horizontal table. The coefficient of static friction between the block and the table is mu s. So we have mu s here. A light string is attached to the block on one side, passes over a small frictionless pulley at the edge of the table. A hanging mass, big M, is attached to the other end of the string and hangs vertically, as shown in this figure. This is figure 1. On the opposite side, the block is connected to a spring with a spring constant K, which is attached to a fixed wall. The spring is initially either stretched or compressed, depending on the block's position. The system is in static equilibrium, and the string remains taut. So what's happening here is the net force is 0. That's what equilibrium is. And, the tension is there. The block can be moved slightly left or right on the table before it begins to slip. Let x equal 0 be the position of the block where the spring is unstretched. So this is going to be x equals 0 here. Positive x is to the right. The block is slowly moved to the right until it's a maximum stretch of the spring, for which the block doesn't move when it's released. So we're going to move this thing over to some position, x max, right? So the block's now going to be over here. And then when we release it, it's not going to move. Okay? Derive an expression for x max. So this might be a little unusual. You might be like, ooh, Alan, like, what's happening? I don't understand what this question is asking. And yes, I made up this question, so it's a little bit, but I think you'll understand what we're doing here. So we're going to move it right a little bit. Now, what happens if I move it too far to the right? Why would it begin to slide? Like, why is there a maximum to begin with? That might consider. Well, the more I push it to so let's draw our free body diagram for block M here. So we're going to have mg, and then we have a surface. Well, so let's do the surface last, because there's a frictional force. So there's a tension to the right. There's a spring force to the left. And then there's the surface touching it, right? So there's a normal force. And now we have to think about the frictional force. Now the frictional force is so what happens is the more you move it to the right, what's changing is the spring force is going to increase, right? The tension is not necessarily going to change, because if you do the big M free body diagram, you'll have mg acting down. And if you look at what's touching it, just the rope, you're going to have a tension here. Okay, so like this isn't really changing because the acceleration is 0. So on this side, we know that mg has to equal the tension. So the tension is not changing, but the more I move it to the right, the spring force is greater. If I do it too far, the spring force is going to just drag it to the left. So the frictional force is attempting to prevent that. The static frictional force would go this way, because right now we're on the very edge. We go any further, the spring force is going to overcome the maximum static frictional force, and then it will begin to move. Okay? So let's look at our x directions. Our F net equals ma. Our right forces, the acceleration is 0, right? Because it's remaining in static equilibrium. So the left forces equal the right forces. So this is k times x max is going to equal the tension plus the force of friction. The tension is equal to big mg plus the force of friction. K times x max. Now, we need the force of friction to be less than or equal to mu times the normal force, right? Which is the maximum static friction. So now we got to look at the y direction to talk about the normal force, right? So upward forces equal downward forces is Fn just equals mg. So therefore, our frictional force, which you can look at as kx max, or you can say, another way to think about it is at the maximum stretch now, we want to be right on the edge where the frictional force is at maximum. So FF is going to equal the maximum when we've stretched it the most. So therefore, you're going to say kx max plus mg plus mu s times Fn. Actually, these are equal to each other. Sorry. I'm just using this equation, but plugging this into here. And so your x max will be mg plus mu s Fn over k. Oh, normal force equal to little mg. Right? Okay, so there we are on that one. Now the block is slowly moved to the left of the equilibrium position. So now we're over here somewhere. And so what's different, derive an expression for x min, the farthest distance to the left the block can be placed while still remaining at rest. So what's going to be different in our free body diagram is that now you've squished the spring, and the spring is trying to push it away, right? Try to push it outward, but friction is going to be opposing it. So what's going to be different here is, if we draw a free body diagram, mg, we have normal force, we still have the tension force to the right. Now the spring force is to the right, and what's holding it in place is going to be the frictional force. And at the very maximum, right? The right and left will match. The T plus the spring force has to equal the frictional force, which we want to say is at the maximum, okay? And the spring force is going to be K times X min is equal to F max, which is mu times the normal force. So the tension is still equal to capital Mg, because that part hasn't changed. The hanging block is still there, still hanging, is equal to mu s and the normal force equaling little mg. So when we solve for x min, you're going to move this guy over, divided by k, like that. Okay. Now, should x min be positive or negative? I just cared about the magnitude, that you understand. It's technically a negative value, so you can put a minus sign here in front if you want. Okay. So that would be the expressions there. Okay. Centripetal acceleration. Let's talk about circular motion, gravity a little bit. Centripetal acceleration is whenever the velocity changes directions. Our process doesn't change. Free body diagram doesn't change, nothing like that. The only thing that's different is we have a centripetal acceleration formula that's directed towards the center of the circle. So if something's moving in a circular path, we have that acceleration to keep in mind. Sometimes we could find the period by just saying, look, I just think of this as this is the speed, is the distance over time if you're moving in a circular path, and the distance is the circumference of the circle divided by the period. So you can rearrange that to find the period. It's not very complicated. The speed is just the circumference of the circle divided by time if it's moving in a circle. The centripetal force is the net force causing the centripetal acceleration. So when we do F net equals ma, the centripetal force that's causing the mv squared over r, this whole thing, there's not a new force. This whole thing is called the centripetal force, right? The whole net force. Not just the part directed towards the center of the circle, the sum, the total force, right, that is directed towards the center of the circle. So there could be a force pointing away from the circle. That's part of the net force. You just ignore anything tangent to the circular path there, right? But the centripetal force is not a new force. Not a new force. Can't emphasize that enough. Newton's law of gravity, okay, is if you are far, right? It's not equal to mg. It's equal to mg when you're close to a surface of the planet or you're not changing altitudes very much. But if you're talking about planets, you're traveling very far from the Earth, force of gravity actually does decrease. And that's the Newton's law of gravity. Gravitational field, or the acceleration due to gravity, is just you just divide by the mass of the object itself. It's the force per unit mass, or it's the 9.8, the acceleration due to gravity, and density is the ratio of mass to volume. So let's do a circular kind of gravitational problem here. So we have small satellite of mass m is placed in a circular orbit of radius r0 around a planet of big mass big M. The only forces acting on the satellite are gravitation and a small drag force from the planet's upper atmosphere. So a little bit tricky. We're going to throw in a drag force problem, which has a magnitude kv, where k is a positive constant and v is the satellite's instantaneous speed. Express all algebraic answers in terms of m, big M, so this is satellite M, k, rho, and fundamental constants as appropriate. Derive an expression for the initial speed of the satellite v0 when the satellite is in circular orbit of radius r0. Begin your derivation by writing fundamental physics principle or an equation from the reference booklet. So right now, there's no drag force at this time. All right, we add the drag force later on. So right now, we have no drag force. So the only thing we're going to do is, if you're not sure where to start, just start with the free body diagram. And the only force acting on it right now is just the force of gravity. Okay? Because nothing's touching it, right? So now instead of using, so we do F net equals ma, and so we only have one force. Now what kind of acceleration is experiencing? Well, centripetal acceleration, because it's moving in a circular path. So this force is g, mass of the satellite, mass of the planet, divided by r0 squared. That's our Newton's law of gravity. That equals the mass of the satellite times v squared over r0, right? That's the centripetal acceleration. Little m's cancel. You can solve for v by canceling out one of those r's and then taking the square root. Gm over rho is equal to v. Okay, that's pretty standard. Did that in AP Physics 1, so that's like not a very complicated derivation. Now let's get into the tricky part, okay? And I haven't done this problem yet, so hopefully it will work out correctly. So we have a drag force that's now introduced. So now, let's say he's moving in this direction. We are going to have a small drag force. It's very, very weak, okay, equal to kV. The satellite is at radius and approximately moving in a circular orbit. Derive an expression for the net acceleration acting on the satellite. So let's look at our free body diagram. How does it change? Well, we still have gravity, but now we have a slight force in this direction, right? And so if you look at the net acceleration, we're having acceleration in this direction and acceleration in that direction. So let's call this, say, the x direction. We'll call this the y direction. So you have a y directional force that's equal to ma, or like if you look at F net equals ma. Let's look at the x direction. You have FD is equal to ma. That drag force is kV, is equal to m. This is the acceleration in the x direction. That's all you can say. In the y direction, you're going to have Fg is your force, and that's going to equal mv squared over r, right? Like some centripetal acceleration. So that's going to be g, mass of the planet, mass over r squared is equal to mv squared over r. Now there's a couple things we have to figure out. We have to figure out what v is. V is, which we already solved here before, right? So the m's cancel. So the v is going to be square root of gm over r, just like it was before, because we're still moving in a circular orbit. So that part is true. Now the ax direction we can now figure out. It's kv over m. So it's going to be k times this velocity, right? Because now we know how fast it's going, divided by little m. And then the acceleration in the y direction is going to be the centripetal acceleration, v squared over r, right? So we're going to just say this guy, gm over r, which is going to be gm over r squared. So now you have an x and a y component. And so the total acceleration, the magnitude, the net acceleration is going to be this. This should have been magnitude. I wanted magnitude here. So you're going to do the ax component squared plus the ay component squared. So that's going to be square root of this thing squared. So that's going to be k squared over m squared gm over r plus this thing squared. Yeah. So this is going to be g squared, big M squared over r squared, like that. And that would be, you could do some factoring if you wanted to, but that's perfectly fine the way it is there. Okay. All right. Let's see. All right. The satellite continues to spiral due to the atmospheric drag. On the following axes, sketch a graph of the speed velocity as a function of time. Okay. Label any important features of your graph, indicate the direction of curvature. Assume the satellite does not reach the surface of the planet during the time shown. Okay. So now what we're going to talk about is we want to talk about the speed. How is the speed going, right? So he's going to be, there's a couple of things as a function of time. It's going to be gm over r, but we should solve for the radius. I think that would be important to know as a function of time. Well, let me think about this one. So to do this, we're going to want to understand a couple of things with the drag force. Remember, with drag forces, you're probably going to do a differential equation. So this thing is controlling the speed, right? The y direction, there's no speed in the y direction. It's only moving in the x direction. So therefore, we know the dv dt, the acceleration, is kv over m. And so now we do need to make sure we get the directions right. There's a negative sign here because the velocity might be this way, and the drag force would oppose that, right? So if we made left the positive direction, then technically the acceleration is negative. So we'll say velocity is positive, but the acceleration is actually negative. So we have to put a negative sign here. And then we solve this as a separation of variables, is negative k over m dt, right? Then you integrate both sides. You get ln absolute value of v is equal to negative k over mt plus c. And then we'll put e as the base, right? So it'll be absolute value of e is equal to e to the negative k over mt, e to the c. When you change that to an arbitrary constant, it can be positive or negative. So you can make this c e to the negative k over mt. So what's going to happen is the velocity is going to decay to zero. Like if you look at the velocity as a function of time, he's going to decay to zero basically. And so that's what happens with the drag force, right? It's going to start off with some initial velocity, and then you're just going to say it's going to decay over time, because that's what drag forces do, because that's the main part. Now, it is true that the radius is going to change, so that will cause a decay in the radius, but ultimately the drag force is just like it was. It's just weird that it's in a circular path, but the velocity is going to decay like that. Okay, so it's concave up, Or you don't have to indicate direction of curvature, just sketching it out is usually enough. Okay. Later, the satellite's orbital radius is decreased to R1. Derive an expression for the time it took for the satellite to spiral from R0 to R1, assuming the orbit remains approximately circular during the transition. Express your answers in terms of this and fundamental constants as appropriate. So that's where we look at our equation, right? So we know what our velocity, we know at the start at R0, we know our velocity ought to equal what we derived in part A, which was square root of gm over rho. All right, so that's the initial velocity. And at R1, the velocity ought to be square root of gm over R1. Okay? And then we just have to look at this equation. So let's look at our general velocity equation, CE to the negative k over mt. So at time, we'll say 0, we're at v is equal to v0. So we'll have v0 equals CE to the negative k over m times 0, which is c. And that's going to equal square root of gm over r0. So therefore, our velocity equation is square root of gm over r0, right? Because that's our c. E to the negative k over mt. And then we want to know when does it get, what time does it get to v1? V1 would be the same equation. It's going to be this one here. So we want to know the time. We want to solve for the time that it takes to get to there. So square root of gm over r1 is the velocity at there over r0, e to the negative k over mt. Okay? And so that's going to be the time it takes, this time here, because this is the velocity of v1, this is the velocity of v0. We're then going to divide the two. So when I divide the two here, you're going to get square root of gm over r1 over square root gm over r0 equals e to the negative k over mt. The g and the m's cancel. This becomes square root of r0 over r1. Okay, then you just take natural log of both sides to get rid of the e. And then, yeah, this becomes r0 because it flips, right? It's reciprocal. And then you multiply by negative m over k, ln square root of r0 over r1. It's going to equal the t. So it'll look like that, okay? So we're using our answer from our derivation a bit from part B for drag forces to then figure out the time it would take to go into that new radial orbit. Okay. Last thing that's kind of interesting is Gauss's law of gravity. So for those of you doing E&M, you'll know Gauss's law for electromagnetism. This is sometimes called Gauss's law of gravity. But if you have a uniform shell of mass, okay, here's the idea. Okay, just in case you've never seen this before. What happens, and this is hollow. This is hollow. Anywhere inside of here, doesn't matter right you're at the center or not, anywhere in here, the force of gravity is 0. And that's because the force of gravity is made up of all these little chunks, and they're all pulling towards you in a way. And it just turns out, and the math is a little tricky, but hopefully intuitively you can see, if you take all of those masses, those little chunks in here, as long as it's uniform, same mass across the ring here around the shell, they will sum to 0. Okay? So that's why if you're at the center of the Earth, if you're dead center of the Earth, and let's say there was no lava to burn you up, like you wouldn't have infinite gravity, okay? Because you would actually have no gravity. All the mass around you would pull on you, and so the net force would actually be 0. You'd be weightless there. The result of this is when you're inside a planet, you ignore any mass beyond the radius if it's kind of a uniform, as long as it's the same amount of mass everywhere around you. So if you're inside a solid planet, and I want to know the force of gravity here, I only consider any force of gravity within this sphere. Everything outside you think of as a shell, and so you only think of the portion of the masses within this spherical shell, this spherical radius here, when you're doing Newton's law of gravity. So it's a modification, or just a making sure you understand how to use Newton's law of gravity, is that this m might refer to just the inner part, because anything outside, all of this stuff, the net force will add to 0. That's what the Gauss's law for gravity is going to tell you. Okay, so let's take a look at an FRQ. So we have a planet of radius r. Planet's mass is spherically distributed with a radial density by this, where r is the distance from the planet's center, rho 0 is a constant. A narrow tunnel is drilled from the planet's surface to the center. A small object of mass m is held at rest at various distances. Express your answers in terms of r. Big R, little r, rho 0, and fundamental constants appropriate. Derive an expression for the total mass m. So this is you breaking it up into concentric shells. So the way you want to think about it is to say, like, look, because the density is radial, in order to add up the masses, I got to think about like a thin shell here. Okay, that has a thickness of dr. And I want to think, what is the mass of that shell? That little dm of that mass of one of those shells. The reason I pick a thin shell is because every piece of that shell is now the same distance r away. So the density is uniform across that shell. So if I make a spherical hollow shell, very thin, because it's so thin that the radius doesn't vary, because it's a thin shell, that the density is pretty uniform. So this is density times the volume. And the density is going to be rho 0, 1 minus r over big R. And the volume is going to be the volume of the shell. Now, it's not the interior volume. It's just the shell. And that volume, if you could flatten it out into like a really thin sheet, it's going to be the area, the surface area of a sphere, times how thick it is. And that would be dr. So that would be the mass. So then we would integrate from 0 to big R to find the total mass. And this is... you're integrating over dr. So let's pull out the constants. 4 pi rho 0 is a constant. 0 to big R. You have r squared, so it's going to be r squared minus r cubed over big R dr. So this is 4 pi rho 0, 1/3 r cubed minus 1/4 r to the 4th over r from 0 to r. That's going to be 4 pi rho 0, 1/3 r cubed minus 1/4. Big R to the 4th over R is going to be also R cubed. So that's going to be 1/12. So this part here is going to be 1/12 R cubed. Times 4 is going to be 1/3 pi rho 0 R cubed. Okay, so that would be the entire mass. Derive an expression for the magnitude of the gravitational force exerted on the object, which is located at a distance r less than r from the center of the planet. Okay, so now what we have to think about is, if we're located a distance r here, we have to think about just the mass inside that shell. Okay, we don't want to think about the entire planet because everything outside of that little r is not going to count. All right, so when you're doing so when we put it together, right, the force of gravity is g times, we'll say, I'll put quote unquote mass over r squared. But this mass is, again, just interior, right? We ignore all of that part. So how do we get that mass? It's almost the same setup as here, right? We take each of the shells, right? Rho 0, 1 minus or big R, 4 pi r squared dr. However, we're not going to go all the way out. We're going to go from 0, all the shells from 0, not to big R, not to the very outer edge, but only to little r here. That's probably the only difference here. Now, I know this is not good notation because we use the little r here and the little r here. Math teacher will get mad at me, but that part's actually okay. So we did the integral already, so it's going to be this thing. It's going to be 1/3, and you're just going to plug in little r instead of big R, minus 1/4 r to the 4th over big R. And so you can factor out an r cubed if you want. 4 pi r0 r cubed, and it'd be 1/3 minus 1/4 big R, little r over big R. That would be the mass. And so the force of gravity is going to be g times that mass, 4 pi rho 0 r cubed, 1/3 minus 1/4 r over big R, all over r squared. That's going to cancel, so you just get this 4 pi g rho 0 r, 1/3 minus 1/4 r over big R, like that. Okay, at a later time, the object moves a point outside the planet, distance r greater than r from the center. Derive an expression for the magnitude of the gravitational force. So this one's a lot easier because once you're outside outside out here, you just do the entire mass of the planet, which we said is 1/3 pi rho 0 big R cubed m over r squared. Okay. If the density as a planet has a uniform density of rho 0, but the radius of the planet remains the same, how would the gravitational force in part B change? So how would the mass change ultimately? Right? So we're going from r0, which is 1 minus little r over big R, to rho 0. That's an increase, right? Because this is, when you do 1 minus, this is some number less than, this is going to make a number less than 1. And if you just make it rho 0 the whole time, it's just going to be a bigger density. Increases the density. And increasing the density increases m, the total mass. And so that implies that increase in total mass increases, so the FG will increase. Okay, so that one's pretty straightforward. So the tricky part was just to making sure you understood the different aspects of adding up shells here, as well as finding the net gravitational force when you're inside a planet.